Alright, welcome back to our proof slides. We're finally going to finish them this time. And oh man, am I excited, because we have some very, very cool proofs that I finally get to show you. They're just very classic and everybody needs to learn them. And I'm excited to be the one to teach you. So the very first thing I want to do though is give you a question that involves proof by contrapositive. So proof by contrapositive, it's just direct proof. You're going to prove an if-then statement, but you're going to take something and then create its contrapositive and then prove that using direct proof. You're going to notice this, create the contrapositive, assume this, prove that. It's equivalent, and it will work out a little bit better this time, okay? So this is my question for you. You're not ready for it yet, so I have to talk about the next slide first, and then I'll send you off and we'll do it. But you're going to prove this by contrapositive. So for any integers x, y, and z, if x divides y and x does not divide z, then x does not divide y plus z. So let me make this into math for you. You are welcome. And then we're going to go to the next slide and come right back, and then I'll have you try this. All right, so for any integers x, y, and z, so for all x, for all y, for all z, all right, if this is true about them, if x divides y, if x divides y and x does not divide z, that's what that stands for, x does not divide z, then x does not divide y plus z. And a good reason, if you don't know, to try the contrapositive with this one is you have a lot of negated divisibility assumptions and conclusions, and we talked about what it means to be divisible. We didn't talk about what it means to be not divisible. Like, you would negate all this, I guess, but it doesn't really give you any useful information. It's very, very nice when you have something divide something else, not something does not divide something else, okay? So with that in mind, let's see if we can transform, using contrapositive, these not divides into actual divides, all right? But we're going to need a little trick. Contrapositives, because we have multiple hypotheses. We're anding together two things. There's a secret. If you have multiple hypotheses, you can change how the contrapositive works. So yes, P implies Q is equivalent to not Q implies not P. That's fine. You could have swapped all these, like the contrapositive of this is like swapping this at the front and negating this at the back, and also negating that as well. That's fine. That's the contrapositive, but there are other forms of it, all right? But what if, like, your if-then looks like this? Two things added together implies this. So if we make the contrapositive, it would turn into this. Not R implies not P, the negation of P ended with Q, which, if you bring in De Morgan's rule, creates this. Not R implies not P or not Q. And what that's trying to say is, right, if R is false, then either P is false or Q is false. That's how you could read it. But there are other equivalent things that involve still an implication. If you would like, you can move one of these hypotheses back, one of these conclusions, if you OR them together, back to the hypotheses, okay? If you think about it long enough, like, what is this, not P or not Q? That's essentially P implies not Q, right? This becomes not R implies not positive P, normal P. Not R implies P implies Q, and you can end up bringing this back to the left-hand side as just P, and you AND it with your original hypothesis. So if you build up the truth table, I promise, this is equivalent to this. You could bring the P back. You could also bring the Q back, and you end up negating it. So this becomes not R and P implies not Q. So if R is false and P is true, then Q is false. That is apparently equivalent to this, which is weird to think about, but if you build out the truth table, I promise it works. So that's something we're going to want to do here. Okay, so let me create the contrapositive for you, and then I'll tell you what to go off and prove. All right. So let's see here. So let's create the actual contrapositive. This would end up being, let's forget about the for alls. I don't want to write them a bunch of times. Let's pretend I'm writing them. So I'm going to negate this, and that becomes my new hypothesis. So x divides, right? Negation of does not divide is just divides, right? X divides y plus z, that's the negated conclusion, implies the negated hypothesis. So negate x divides y, and x does not divide z. So we can use De Morgan's rule on this ending part, and we end up with x divides y plus z still implies not x divides y, so x does not divide y. Or, right, because De Morgan's rule, and then the negation of this one. So x just divides z. Okay? So this is nice. This is the contrapositive, but we still have a not divides, and that doesn't really help us at all. We would like to make that a divides if possible. And the trick that I just showed you is we can bring that back, because we have an or here. We can bring back this its negated form into the hypothesis. All right, so this ends up being x divides y plus z, and x divides y, because I can take this, bring it back into the hypothesis as its negated form. If you negate does not divide, it becomes just normal divide. And then that all implies the other thing, x divides z. And that's the easiest thing to prove. Okay? So that's what I want you to prove. For all x, y, and z, this. Try it. And then I'll do it for you. So here's the proof. Hopefully you got pretty far on it. For all x, y, and z, we assume this, right? And prove that. It's just a direct proof again. We just had to make the contrapositive, a certain form of it. Okay? So assume, let's get rid of the quantifiers. Assume x, y, and z are integers, because that's part of the first thing. That's what they quantify over it. Assume x, y, and z are ints. And then we also assume some other things. We assume these hypotheses, right? Assume that x divides y plus z, and assume that x divides y. We use those to show this. So, and x divides y plus z, and x divides y. Isn't that nice? Now all we need to show is this final fact from all these assumptions. What we need to show to prove this theorem is that x divides z. Okay? Alright, so let's unpack some definitions now. If I know this and I know this, what does it mean according to the definition of divides? Right? If you go back up to that previous slide or check your book, here's what that means. So if x divides y plus z, that means you can make y plus z by multiplying x by some integer. So y plus z equals k times x. It's some multiple of x. And if x divides y, then I also know that for some other integer, y is equal to x times some other thing. So let's call that m times x. All right? For some ints, k and m, that's what divisibility means. So I'm unpacking those definitions. Now I have some equalities, which is nice. And I need to show this. I need to show that x divides z, and what does that mean, right? According to the definition. What we want out of all this to prove our final theorem is that, like, z is equal to some other thing, some other integer, call it r, times x. If I show this, that means x divides z, okay? That's what that means. That's what we want, and so let's go and get it. So how can we end up with that? So let's see what we got. Y plus z. I know that y plus z is this. Y plus z. Let's see here. I have, well, I know what y is. Y is m times x. So y plus z is the same as m times x plus z. Okay, that's a good start. What is that going to give me, though, is the next question. I also know, right, y plus z is equal to kx, right? So if I do this the other way, it's equal to k times x. Yeah, so these are all equalities. These are all the same. Does that make sense? So this is, I could just put it over here as well. K times x. So not only does y plus z equal, if you substitute y with m times x, it equals that, it also equals kx, right? So those two things are equal, these last two things are equal. And now I can solve for things. I can take this equation, and I can bring all the x's on the same side. So let's, I don't know, or maybe we can get z by itself, which involves getting all the x's on the same side. So let's subtract both sides by mx. And then I end up with z is equal to kx minus mx. and I can factor out an x there. That's equal to k minus m times x. And think about what I need still, right? I need to show that z is equal to some integer times x. Doesn't matter what the integer is. What have I just done? Ooh, z is equal to some integer times x, because k is an integer, m is an integer. If you subtract integers, you're still left with an integer. Call that r. You see how the proof goes through there? That's an int. Subtract two ints, you still got an int. So, let's write that all out. So z is equal to k minus m x. K minus m can be our r that we were looking for this whole time. And k minus m, it gets to be our r because it's an integer. K minus m is an integer. Is an int. So there's a lot of little side conditions you need to keep track of, but it all follows. So, and k minus m is an int. So I found an integer, multiply it by x, I get z. That proves, right? That's what we need to show in order to say that x divides z. I found something you can multiply by x and get z. That was an integer. All right, so x divides z. That was my conclusion. After all those assumptions, this was a direct proof. I ended up with my conclusion after assuming my hypotheses were true, after forming the contrapositive, and oh man, that's what I needed to show. So QED, mic drop, on to the next proof. Okay, so definitely study this one. It is a good one to take a second look at, all right? But I promise eventually this will start making sense that you could do these from scratch. Definitely come back and try them yourself if you're getting stuck, okay? After you watch me do it, see if you can do it too. All right. So here's a new question for you. So let's see here. I think this will be slightly easier because it's just a single hypothesis implies a single conclusion. So here it is. Prove this by contrapositive. For every non-zero real number x, remember real number means numbers that can maybe include decimal places. If x is irrational, then 1 over x is also irrational. Interesting. All right, so here's a for all, and x is rational. If x is rational, that's going to be your p, right? And implies what? Implies q, 1 over x is also irrational. That's going to be the q of our statement. So if this, then that. If p, then q. All right, and this is easier to prove if you create the contrapositive, because we don't know a whole lot about irrationality. We have some definitions though about rationality. Ooh, we know that the number is a ratio of two other numbers. That would be nice if we could put it into that form. So let's get there. Let us use it. So create the contrapositive of this and try to prove it, and then we'll come back and I will show you my way. So getting rid of this for all, which is kind of implicit, we're getting used to that. Here's the original proof, right? If x is irrational, then 1 over x is also irrational. The contrapositive is negate this implies negate that. So negate the conclusion. If 1 over x is also irrational, so that's 1 over x is irrational, negate that. Just that gets rid of the ir part, right? If you negate 1 over x is irrational, you end up with 1 over x is rational. You see how that's the negated form of the conclusion? Implies the negated form of the old hypothesis. That's the contrapositive. So if x is irrational, the negated form of that is x is rational. So we're saying that's not true. So x must be rational. So this is the contrapositive, and now we can prove this. Assume this, prove this. Ready? Proof. We have assume 1 over x is rational. Assume x is, also we have for every non-zero real number x. So we also assume that x is non-zero. Assume x is non-zero. So that's going to help because we can't divide by 0, right? And 1 over x is rational. What we need to show, we need to show that x is rational. X by itself. Take the reciprocal of this, I guess. To show x is rational. So what does it mean to be rational? Unpack that definition. If we know that a number is rational, and we do have a hypothesis about that. If we know a number is rational, then there are two numbers, two integers, x and y, such that y is not equal to 0, and x over y is equal to that original number. Okay? So that's how you can unpack rationality. You know that that number is made up of two numbers, and it's a ratio of them. All right? So if I know that 1 over x is rational, that means, 1 over x must be the ratio of two integers. 1 over x must be m over n for some m and n where n is non-zero. Some m and n are ints, and x is non-zero. Or sorry, n is non-zero, excuse me. We already know x is non-zero. We're assuming that. N is not equal to 0. Let's just write it like that. So that's what we know based on our definitions. And now we need to show that x is rational, so that x is a ratio of two numbers. So can you get x by doing this? What is x but 1 over x, right? It's just the reciprocal of 1 over x. But x is equal to 1 over x, right? That's fine. But what is 1 over x but m over n? Ooh, x, which is equal to, so this is really 1 over m over n, and that is just by math equal to n over m. And you can do that because we're assuming that things are non-zero, okay? So that's fine. I can get this equation now. So x, I know, is equal to n over m. And because, I need to show that x is rational, which means showing that x is a ratio of two numbers, and they are the thing on the bottom is non-zero, all right? So I need to show that that it's a ratio. I need to show that m is not 0, okay? So let me show you that. So 1 over x is non-zero because, right, assume x is non-zero. That means that 1 over x is non-zero. That's fine. So I know that. And that means if you take the reciprocal of a non-zero number, you still have a non-zero number, right? Maybe got bigger or smaller, but you can't, there's no difference. Same for m over n, right? Because that's what 1 over x is. That's equal to m over n. So those are all non-zero, and that means it all works out, right? So this was non-zero. We took the reciprocal of m over n to make n over m. That's still non-zero. So that means that the bottom part was non-zero as well. Okay? So m is not equal to 0, so x is rational. I hope that makes enough sense. There are a lot of little side conditions that we didn't talk about, like, does it make sense that 1 over x is non-zero if you know that x is non-zero? That's just some math rules, but that's going to end up giving us what we want. Okay, so x must be rational, QED. End of proof, mic drop. All right, so we just showed that it kind of makes sense unfolding the definitions. Like, you just make the reciprocal of this and show that you're not dividing by 0, and it all works out. So that is another proof by contrapositive idea. And now I'm ready for like the most interesting way of proving things that we'll learn in these slides. It's called proof by contradiction. It's not the same as proof by contrapositive. It's very, very different. It is very powerful though, right? So proof by contradiction is using false somehow to help us prove that things are true. It's really weird. I'm going to show you why it works. But here's the proof by contradiction strategy. It's slightly similar to direct proof, but very different, all right? So here is the proof by contradiction. Assume your entire theorem, which maybe itself is an implication. Assume the whole thing is false. Assume that the thing you're trying to prove is false, all right? And then find what's called a contradiction from that, all right? So let's say that your entire theorem statement, the thing you're trying to prove is Q. What you do is, if not Q, then false. That's what you try and prove instead, all right? And I promise that this works, that this is valid. So this is what you prove. You prove that, all right, assume that because this, you now just prove this as a direct proof, assume that your entire theorem was false, and then show that you can prove false. Prove that false is true, which is what's called a contradiction. That doesn't make any sense. False could never be true. But under this assumption, which was supposed to be the wrong assumption, we found that false is possible, and that's just wrong, okay? So here's the idea. let me try and prove this to you. So you assume the negation of your theorem, and you try to derive that false is true, which is a contradiction, because, like, I don't know, you show that false is equal to true. And of course it's not supposed to be. That's called a contradiction, right? And this is the theorem setup. Assume that your entire theorem is false, and try to derive that false is true. What is this? What's the same? What is this the same as? This is, well, I can get rid of this implication by saying, negating this, it's not this or this, right? Not Q or false. If you or by false, that does nothing. So that's equivalent to not Q. And then double negation gives you just Q. So really, this really was equivalent to proving the same theorem. Isn't that neat? Another way to show that is you take this and you make the contrapositive of that. True implies Q, and that's the same as just Q. Because if you have true implies Q, that's the same as not true or Q, which is the same as false or Q. And for the same reason, if you're ORing with a false, you end up with just Q. So two different ways of showing you that this is equivalent to the original theorem. Isn't that neat? So if you just prove this instead, sometimes, and a lot of times, it's easier, all right? This equivalence makes no sense at all because you're showing something that makes no sense, okay? Your goal is to prove that false is true. It's very odd, all right? But the way you can end up with that, you prove something that is weird. You show that false is true because of something like this. This is how you get at false, all right? False comes in the form of, like, you have some statement P, and you also have at the same time, you've proven both that P is true and P is false, right? Which is contradictory. They can't be, it must be one or the other, right? Something is either true or it's false. It can't sometimes be true, sometimes be false in logic. So if you ever have this, that is equivalent, using our rules, right? That is equivalent to false. It's impossible to be in both of those statements. That's a contradiction. So once you end up with something like this, you have just proven that false is true. You've just proven false. You've derived false. And that's it. Then once you have false, the entire theorem follows, which doesn't seem right. It seems like there's something left to be done, but you really are done. And so that's why people call it an indirect proof. It feels a little weird, like it shouldn't be correct, but it really is. I just showed you why. Okay, a bunch of different ways. Assume your theorem's false, derive false. Prove that false is true. All right, let me give you some examples. It's very weird, but it is very, very powerful. Okay? So here's a cute example involving birthdays. There's about 25 people in this class, so let me show you something interesting about that. So among any group of 25 people, so the people in this class and me or something, there must be at least 3 of those people who are all born in the same month. That's kind of weird. Let me show you that this is a true statement. All right, let's prove it by contradiction. And let's see here. So let's take this and figure out what its negation is, because we're going to assume, right? Proof. It's going to be by contradiction. We usually say what we're doing. And let's figure out what it means to negate this. So among any group of 25 people, there must be at least 3 who are all born in the same month. So we're showing that there must be a month. There must be a month, call it, I don't know, call it M. There must be a month called M such that there are greater than or equal to 3 people born in M. Greater than 3 people in this group born in that month M. Okay, so that is the original theorem. So there exists a month such that greater than or equal to 3 people were born in that month. That's the same as this theorem. To prove the theorem by contradiction, we're going to assume that our entire theorem is wrong. Assume it's false, and then derive false. All right. So to negate this, this there exists, it becomes. Let me draw a bigger arrow. It becomes, well, if you negate a there exists, you get a for all, right? So for every month M, it better be the case that less than 3 people were born in that month. Less than 3 people were born in M. You see how this is the opposite of this original idea? So if there isn't a month where there are at least 3 people born in it, that must mean that for every month, less than 3, strictly, people were born in that month. All right? So now we can prove it by contradiction. So let me walk you through it, and hopefully you'll gain some knowledge by osmosis. So here's how I'll walk through this proof. So I need to prove this. So let's start with a group of 25 people, because that's the first thing we're kind of technically quantifying over. So let's call that group of people G. Let's give everything a name. Let G be a group of 25 people. All right. And now, here is the proof. Assume this is all true about every month, because that was the negated thing. We're assuming that the theorem was false. Assume that for every month less than, strictly less than 3 people were born in that month. So assume, because that was the negated theorem. We're assuming that the original theorem is wrong, and we're deriving a contradiction. So assume less than 3 people in G were born in each month. All right, then can you see how you might derive a contradiction, something that doesn't make sense out of this? Think about it long enough. Then, if that's true, then the maximum number of people in G is bounded by this idea. There's 12 months, right? And there's less than 3 people born in each month. So then the maximum, the best you could possibly do, the largest the group could possibly be, the max number of people in this group then, if we're assuming this, the max number of people in G is assume like we've got people born in every month and they're right up against this rule. It's all less than, right? Less than 3, so let's say the max is 2, right? The max number of people in G must be then, you see how it's 12 times 2 equals 24. Ooh. And right there, that's the problem. You see it? 24. The group has 24 people, but we just assumed that G holds 25 people. We just proved that 24 equals 25. Do you see that? So we just proved that 24 is equal to 25, which makes no sense. That's your contradiction. You see that? We just proved something that is contradictory. And at this point, we have proven the original theorem. We just say, all right, something makes no sense. We've just proven falsehood. This is called a contradiction. People legitimately say this in their proof. They say contradiction with an exclamation point, and then like that's the end of the proof. QED. Other times, people like to, instead of writing contradiction, they write a little lightning bolt symbol. You might see that. It looks like this. They write a little lightning bolt, and that is showing that they just derived a contradiction. All right? So that's the idea. That's proof by contradiction. It seems like it doesn't make any sense at all, but it really is valid. So assume that your theorem is wrong and derive a contradiction. That's equivalent to proving the original theorem. All right? So we just did that. We found a contradiction, and that proves the original theorem. Beyond a shadow of a doubt, now that we know, we found a contradiction. If we assume that the theorem's false, that means the theorem must have been true. Does that make a little bit of sense, hopefully? So we know that among any group of 25 people, there must be at least 3 who are all born in the same month for this reason. Okay? That is the idea. So there's at least 3 of us all born in the same month. Isn't that fun in this class? So, let's see here. Let me show you a cool fact, and then that will help us prove a theorem. So here we go. If you have this, like if this is your theorem, like you have some big implication that involves a bunch of hypotheses ANDed together, if you have A and B and C implies D, and you try to negate that, usually because you're trying to do proof by contradiction, this ends up being equivalent to A and B and C and not D. So take everything from the hypothesis and it together with the conclusion, having negated that conclusion, all right? And so the reason this works is if you take this and you use De Morgan's rule, you're going to shove this into here. So first of all, you're going to translate the implication to just not in an or, not hypothesis or with conclusion, using our normal equivalence rules. And then we're going to start bringing in these negations. So here's this negation. Let's bring it over this or using De Morgan's rule. So we're going to negate this side, negate this side. So we have a double negated left side. The or flips to an and we have a negated right side. All right, but what is a double negation but nothing at all? That all goes away, and now we're left with the original hypothesis ANDed with the negated conclusion. Okay? And A and B and C could have been anything. They could have just been one statement. All right? So like that means P implies Q. Try to negate that. That's equivalent to P and not Q. That's the one way to make it false, right? P is true, conclusion is true, and the hypothesis is true and the conclusion is false. I always get those mixed up. But this is why. So if you have to negate some sort of long implication, you can transform it into this. Okay? That's the idea. And so now I'm ready to show you probably one of the coolest proofs in this class. It is a classic example. Everybody needs to learn it. It's just so magical. It's proven in a way that you wouldn't think to do it, and it is a proof by contradiction. It just all comes together. It's so nice. It's lovely. It'll blow your mind. So let me prove to you that the square root of 2 is an irrational number. First of all, what does irrational mean? These are rational numbers, 10 over 20. That's equal to 5/10, or 1/2. I'm going to show you that in a second. But a rational number is one that's a ratio of integers. If it's irrational, that means you cannot have two integers, m on the top and on the bottom, such that this is equal to that ratio. Okay? It's an infinite number. It goes on forever. You cannot find two whole numbers to create it. All right? That is rationality. All right? It's an irrational number. I'm going to prove this theorem. But to get there, we need a little smaller theorem. This is like the big thing. Theorem is like a very strong word. It's like something big that you prove. If you need a little helper theorem, you call that a lemma. All right? So we're going to need a lemma first to help us get at this theorem. So let's prove this one first. All right? Here is our lemma. If x squared is even, then x must have also been even. All right? So lemma is just like a little theorem. You're using it to prove the important thing, which is like square root of 2 is irrational. That's very important. All right? So let me prove to you quickly this lemma. So proof. I'll do it quickly. I won't even translate it to math. So what we're going to do is we're going to prove this by contrapositive. Not contradiction, contrapositive. Contrapositive. And so that means we're going to assume that x is odd. Assume the negation of the conclusion. Assume, because we're going to do a direct proof from the contrapositive. So assume x is odd, and then we need to show that x squared is odd. That's the negation of the hypothesis. That's a contrapositive there. So if x is odd, then x must be equal to 2 times k plus 1 for some k. I won't write that. You know what I mean. K is an integer and all that. All right. After that, let's make x squared, because we need to prove that x squared is odd right now. X squared is equal to, well, if I have this, 2k plus 1, let's just plug it in. X squared is equal to 2k plus 1 squared then, if x is equal to this. So, oops, let me write the plus sign a little bit better. 2k plus 1 squared. And then I can, foil that out, make it all big. That's equal to 4k squared plus 4k plus 1. And what is this? Ooh, I need to show that this is, first of all, I need to show that x squared is an odd number. So I need some number, I need x times an integer, I need 2 times an integer plus 1. And that will prove that this number is odd, right? So let's factor out a 2. So this is equal to 2 times k squared, 2k squared, excuse me. 2k squared plus 2k. And then I still have that plus 1 over here. What is this? My goal, again, was to prove the negated form of that hypothesis. Prove that x squared is odd. What do you know? Well, this is 2 times something plus 1. In order to prove that x squared is odd, I just need to know that this something is an integer, and it really is, right? This has to be an integer because k was an integer. Multiplying integers by integers, it's all ending up with an integer, right? So I've just shown that x squared is equal to 2 times an integer plus 1, which is oddness, right? That's what I needed to show. So x squared is odd, and that is the contrapositive of this original lemma statement, which proves the entire lemma. All right? So I went kind of fast there, but that is my lemma. If x squared is even, then x is even, and I proved that with a contrapositive. So assume this negation and prove this negation. Cool. We're going to need that here. So here is the mind-blowing example. So theorem, the square root of 2 is irrational. I'm so excited to prove this for you. So proof. Here's how you do it. It all falls together. It's so beautiful. We're going to prove it by contradiction. So we're going to assume then that square root of 2 is rational and then derive something wrong happening. Derive a contradiction out of that. So here's how we do it. Assume x is rational. Or sorry, assume negative square root of 2. Sorry. Too many math concepts going on today. Assume square root of 2 is rational. And that's beautiful because we know what it means to be rational. We can unpack that definition. So square root of 2 better be equal then to, let's say, a over b this time. For some integers a and b, if I'm assuming it's rational, it better be equal to two integers, their ratio. For some a and b that are integers such that a over b, and like they're integers, b is not equal to 0. And I'm also going to have a side condition on this. Here's the trick. This is the trick of the proof. For some a and b such that a over b, I can ask this of my numbers. A over b is fully reduced. This is the trick. This is totally fine to ask for. Because you can take any ratio of numbers, you can take any fraction and reduce it to the smallest fraction, right? So square root of 2, if we're assuming that's rational, it's equal to two numbers, one over the other, just reduce that until you can get to the final form. So maybe it's equal, it was really equal to m over n, but that was unreduced. Just reduce it and call that reduced form a over b. That's what I'm asking of the proof right now. That's totally fine to do, all right? So square root of 2, it's a ratio of two numbers. Let's just assume that that ratio is fully reduced. You can do that if it's not already reduced, like you can start dividing by stuff, right? And so that's something like this. 10 over 20, that's equal to 5. You can take out a 2 there, right? 5 over 10, you can take out a 5 out of that, which is equal to, not 5, which is equal to 1/2, of course, right? So this is like the fully reduced form. The rest of these are not reduced. So we're asking for like the 1/2s out of this deal. Assume that if square root of 2 is rational, find me that ratio and reduce it, all right? Reduce it fully. Call that fully reduced fraction a over b, all right? And here's the magic. Well, if this is a over b is supposed to be square root of 2, let's square that. Squaring both sides. That means 2, right? Square root of 2 squared is just 2 equals this squared. 2 is equal to a squared over b squared, right? Because this is equal to square root of 2. Just square both sides. Now I know 2 is equal to a squared over b squared. And I can solve for one of these. Let's solve for a squared. So 2b squared is equal to a squared. That's kind of cool. Okay. What does this mean about a squared? It's 2 times some other number. You remember that definition? That means that a squared must be even. So a squared is even. Okay. Let's see here. What do we know from this? It's just all going to fall through. It's going to be so beautiful. So a squared is even. If I know that a squared is even, I know a itself is even by my lemma. Ooh. All right. By the lemma, that means a is even. Cool. So what does it mean to be even? So a is equal to 2 times k for some k. That is an integer. All right. Now, what is 2b squared? 2b squared is equal to, well, it's equal to a squared. But what is a but 2k? 2b squared is equal to a squared. A squared, or just a, is 2k, so square that. You see how that all works? 2b squared is equal to a squared, but a is equal to 2k, so 2k squared. 2b squared is equal to 2k squared. Crazy. That's equal to 4k squared, of course, if you just expand all that out. And if you, let's see here, if you solve like this side and this side, if you divide by 2, you end up with b squared equaling 2k squared. I'm just going to do some math here. Equals 2k squared. That's fine. Oh, what does that mean about b squared? I have the same idea going on here. I have b squared is equal to 2 times some integer. Ooh, b squared is even. So b squared is even. By the lemma, b is even. Do you see the problem now? All right. So b is even by the lemma. And this is where all the problems occur. So what does that mean for b? Unpack the definition. b is equal to 2 times m for some other m, just like a was equal to 2 times k for some k. This is interesting, because I just said that the square root of 2 is equal to a over b, where a and b were fully reduced. Now this fraction was fully reduced. But we just showed that a over b is equal to 2k over 2m, because a is even, b is even. We can find numbers that we can multiply them by 2 and get those numbers back. A over b is equal to 2k over 2m. What is special about this fraction? I can knock out a 2 from both sides and reduce it further. Ooh, this can be reduced still. That's my contradiction. It wasn't fully reduced. A over b was not fully reduced. Wasn't fully reduced. So I have that a over b is fully reduced, and I just proved that it wasn't fully reduced. To have both is to have a contradiction. Contradiction, QED, mic drop. So no matter what, if you think you have a ratio that creates square root of 2, you really don't. If you think you have a fully reduced ratio that creates square root of 2, you really don't. You can always take off a 2 for some reason in this universe where square root of 2 is actually rational, which doesn't make any sense. That is a universe that does not exist. That's what we just showed, right? By a proof by contradiction. We assumed the negation of our proof, assume that square root of 2 is rational, logically show what follows from that assumption, and then derive a contradiction which proves our original theorem. It's impossible for square root of 2 to be rational, so it must have been irrational. Isn't that beautiful? This is a great theorem. It takes some tricks, like to think, like, let's ask for this fraction to be fully reduced. That's what derives our final contradiction. That's beautiful. That is hard to come up with, but that's why I'm showing it to you. All right? Now I have a question for you. Definitely easier. Okay, it's going to be similar to the birthdays question. So here is a statement. Prove it by contradiction, please. So if you have a group of 9 kids, and those 9 kids among each other, all of them, have won a total of 100 trophies, then at least one of the 9 kids has won at least 12 trophies. So if 9 kids, they're very good at whatever they're doing. You grab a group of 9 kids who are like sports, competing in sports or something, and they have 100 trophies shared between them, in some way. They each won one of those trophies. Then at least one of those kids won at least 12 trophies. Okay, so this is going to come from contradiction. See if you can figure it out. So you're going to negate this entire theorem and prove it. All right, did you give it a good try? Let me show you my proof. So, all right, if a group of 9 kids has won a total of 100 trophies, and at least one of the 9 kids has won at least 12 trophies. So you're kind of like assuming this, and like here is the conclusion. We can negate that. That can be what we use our proof by contradiction on. So, all right, at least one of the 9 kids has won at least 12 trophies. All right, if this is not true, right, assume it's false. Assume that all 9 kids won less than 12 trophies. See how that's the negation of this proof of this statement? Assume, like this is the real theorem statement at the bottom here, assume all 9 kids won less than 12 trophies, strictly less than. Strictly less than 12 trophies. Which means they all won at most 11 trophies each. Okay? Well, that's the idea. Then what happens because of this? What's the maximum number, right? Then the total number of trophies shared among those 100 kids, then the total number of trophies was at most at most 9 times 11, which is 99. So we just showed that the maximum number of trophies that the kids have are 99, but there were 100 trophies total. See how that's a contradiction? So there must have been a very very well-performing child who got at least 12 trophies. There are 100 trophies total. So good for that kid. That's our contradiction. We showed that we can have at most 99 trophies, but there were 100. Okay? Does that make sense? So you can actually use proof by contradiction with parts of the theorem. You can be like, this is an if-then statement. Let's assume this, and then try and prove this by contradiction. That's the idea. So we assume this, and then we prove the wavy bit by contradiction. That's totally fine. You can prove a piece of it by contradiction, as long as it's your last piece. Contradiction. Okay, so that's what we did there. I hope that makes a bit of sense. That's proving by contradiction, and then I have one last, two final concepts, and I think they come together in my last question for you. All right, so let's talk about proof by cases, because a lot of the time you're trying to prove a for all x, p of x is true for that thing, but sometimes it's hard to prove all at once. Like P is true for every single element of the domain. I make that one arbitrary element and it just works out. Sometimes it's hard to prove a for all using just one arbitrary element, because maybe like the domain is a bit different. Like here's my domain. I have some elements over here that like look a certain way. I have some elements over here that look in a different way that are completely different from the first one. And then I have some elements way over here that function differently than the other two as well. So the idea of proof by cases is I can just split my domain into a bunch of different classes, and I can give a different proof for each class. Like I can prove it for these ones. I can prove that the predicate's true for these guys, and I can prove that the predicate's true for all these guys. And in sum, they have proven that the theorem is true for the entire domain. Okay, I hope that makes sense. You can give a different proof for each class. Sometimes it's easier to specialize like that. Okay, so for example, like if your predicate is over all the integers, it's possible that it's easier to give a different proof for all the negative numbers, 0, and then all the positive numbers. Because together, right, together these make all the integers. Maybe it's easier to split up by cases, though. All right, together these cover all the integers. Together cover all ints. That's the idea. And so once you've covered them all somehow, then your proof has gone through. It's true for everybody, right? So here's a quick example of that to use proof by cases. Let's define the absolute value of x to be just the x itself if it's already a non-negative number. If x is greater than or equal to 0, just say that the absolute value of x is x itself. Otherwise, if x is less than 0, make the absolute value, define it as a negative x. And let me prove to you that that's the correct thing. Let's prove that for all x, the absolute value of x is greater than or equal to 0. Okay? We'll do it by cases. Proof. Do you see how naturally the definition of this absolute value has two cases? It's like, all right, here's one case, here's another case. I can prove a different thing for each case. I can prove the theorem itself, prove that it's positive, the result is positive after taking the absolute value in a different way for each case. So case 1 will be two cases, because there's two cases in the definition. So case 1, let's assume that x is greater than or equal to 0. Case 1, x greater than or equal to 0. Let's prove that the absolute value of this number, which is we're assuming to be greater than or equal to 0, is itself greater than or equal to 0. So the absolute value of x in this case, if it's greater than or equal to 0, well, it's just defined to be x itself. So absolute value of x is x, which I have assumed, right? I'm in this case where it's greater than or equal to 0, so the result is greater than or equal to 0. So that covers this case. You see how I just proved that if x is greater than or equal to 0, its absolute value is greater than or equal to 0? That is what's going on there. So the absolute value of x is greater than or equal to 0. And then I have the other case. I have x is less than 0. And together, those two cases cover all the integers. Case 2, x is less than 0. So let's define this. So absolute value of x is equal to negative x, because x is less than or equal to 0. And I need to show that negative x is greater than 0. It's greater. I need to show that this is greater than or equal to 0 somehow. Now let me show you how I can do that. So if I know that x is less than 0, and I'm about to make the negated form of x, right? Because that's what the absolute value does. What does that mean about this original thing that I'm assuming? I'm assuming x is less than 0. The result of the absolute value is negative x. What do I know about negative x? If x is strictly less than 0, if it's a negative number. You just negate, like, multiply this entire inequality by -1. What does that do? It flips it, right? It's like the De Morgan's law, kind of, for inequalities, in a sense. Negative x is greater than 0, just based on our rules for math that we know. So what do I know now? I know that negative x is greater than 0, and I need to show that its absolute value was greater than or equal to 0, right? So the absolute value of x, in this case, is negative x, which I know is greater than 0, and it loses information, but it's still true, right? It's greater than or equal to 0 as well. You see that? If I know it's strictly positive, it's also positive or maybe 0. So in sum, absolute value of x in this case is greater than or equal to 0. That covers this case, and both cases cover all the integers, that one and that one. So it must be true that for all x, the absolute value of x, according to that definition, is a non-negative number, is greater than or equal to 0. Okay, so I hope that makes sense. It was kind of necessary to split up into cases, and that is a normal thing to have. All right, 2 last slides for the lecture today. So I'm going to teach you about WLog. It stands for without loss of generality, and it's very, very useful because sometimes you're proving something, and you're like, all right, I'll split it up into cases. I have this case and this case, and like, here's the first case. I don't know, I'll draw a picture of a human, because why not? Like, here's the first case, and you prove it. And then the other case looks like this, like it is a person but upside down in a sense. And it's kind of obvious that this case is just as true as this case. It's just things are a little flipped. There's no real difference between those two cases, right? So sometimes 2 of your cases, or more of them, are symmetric. And so it's obvious that if one of those cases is true, you can just kind of move some stuff around and the proof for the other case works out, all right? So without loss of generality, just prove one and it all works out, okay? So let me show you that. That's what WLog stands for. It lets you not have to do useless work when it's obvious that, like, this is also true if this side was true. Okay, so here's my proof. So let's prove this. For any 2 integers x and y, if x is even or y is even, then x times y is even. So the idea is, like, if at least one of them is even, either x or y, or maybe both, then multiplying them together is even. All right, so here's the proof. You say, assume, because you can just flip-flop them around, and I'll prove that to you. Let's assume, without loss of generality, that, you know, x is the one that's even. Because it's like, either one of these is even. Let's assume that x is the one that's even. That x is even. X is even. And then I have no information about y. Right? I'm assuming that x is the one that's even. I just know that y is an integer at this point. Right? What I need to show is that xy is even based on that. To show x times y is even. And let's get that pretty quickly from the definition of things. So if I know that x is even, then x is equal to 2 times k for some integer k. What does that mean about xy? Xy is equal to 2 times k times y, right? Because that's what x is. And what do you know? To show that something is even, I just need to show that that thing, right? That thing is equal to 2 times an integer. What is k times y but an integer times an integer? So the result is still an integer, right? Therefore, xy is even in this case. And that actually proves our theorem, because if you think about this long enough, if you do it for the other side, like the other case is that y is the one that's even, then try and prove that xy is also even. The proof goes through just the same, right? Just instead of x, say y everywhere. And this is like x. It all works out. It's all the same, and it was kind of wasted work. It's symmetric, all right? So swapping, I hope you see that. Swapping x and y in the proof on the left proves the other case. Proves the case where y was the one that was even. It's like one is true or the other. Left proves the other case. So you don't have to do both. Just say, assume without loss of generality, if it's obvious that like the proof will go through just as easily for the other side, just assume like x was the one that was even. Because it's obvious that the proof will go through if you change x to y. Okay? That's the idea. And so this proves the entire theorem by just proving one of the sides, one of the cases. That's what without loss of generality stands for. But you have to be very careful. You have to make sure that like it really is symmetric. It really is, there's no difference. If you prove the other side, it's just as obvious. Okay? That's the only thing you have to watch out for, though. So with that in mind, here is my last question for you for these slides. So please prove the following statement by cases. So let's say that you have two integers, x and y. If they have the same parity, then their sum is even. And parity means, same parity means that either the numbers are both odd or they're both even. Okay? So you'll need to prove this by cases, see if you can make it work. So you got two numbers, and assume that they have the same parity, prove that their sum is even. Alright, do you see the two cases? Here's how I'll do it. Proof. We have two cases because, like, if x and y have the same parity, that means they're either both odd or they're both even. And this case cannot be handled without loss of generality, because even numbers are like 2 times something, and odd numbers are 2 times something plus 1. It's not the same proof on both sides. So I have to spell both out, okay? So case 1 is when they're both odd, let's say. And then case 2 will be when they're both even. We'll do that in a second. So assume, right? So if they have the same parity, then their sum is even. So let's assume that they're both odd, because that's one of the ways that they have the same parity. Assume x and y have the same parity. Assume that they're both odd. Assume x and y are odd. What does that mean about x and y? So that means x is equal to 2k plus 1, and y is equal to 2 times something else plus 1. Y is equal to 2m plus 1, let's say, for some integers k and m. What is their sum? X plus y is equal to 2k plus 1 plus 2m plus 1, which, if we do some math, that's equal to 2k plus 2m plus 2. And if I take out a 2 of all of those things, I have 2 times k plus m plus 1, and this is a integer times 2, and that means this thing was even. That's cool. An odd plus an odd is still even, or it becomes even. That's really weird. So x plus y is even. So that's check. That's one of the cases. I have 2 cases though. Case 2. If they are both even, I need to show that their sum is even still. It doesn't like magically become odd or something. This is, I guess, a slightly easier case. I don't have to like take out a 2 or something. Or notice that there's a 1 and like remember to keep the 1 or something. It will go through very similarly though, but it's not without loss of generality. So assume. So the other way that they're having the same parity is if they're both even. So assume x and y are both even. What does that mean about x and y? That means x is equal to 2k and y is equal to 2m for some integers x and m. If I sum them together now, x plus y is equal to 2k plus 2m. And what is that but 2 times an integer plus an integer? Okay? So again, I have x plus y is equal to 2 times an integer. And that just means x plus y is even. That's the definition of evenness. So x plus y in this case as well is even. So that means no matter what, if x and y have the same parity, either they were both odd or they were both even, their sum ends up being even. And so that, with both cases together, proves my final theorem, QED. All right, so that's the statement by cases. Hopefully, this English-looking text is making enough sense to you. Please yell at me if it is not. I want to get you on this level of understanding and writing proofs in this way, where you have the rules from the logic slide deep down in your head, but you're working with English words now. All right? And you're using our fancy tricks like direct proof, proof by cases, proof by contradiction, contrapositive, all that fun stuff. So these are very fancy proofs. I was excited to show you this one especially. But that is all for the lecture today, and just some reading this week, no new lab or homework. So that is all for the week, and I will see you next time.